So first of all, if you happen to see this talk before, then I'm sorry. I'm really pro recycling. So I actually made this talk for a Higher Data conference. So has anyone here been in Higher Data? You can leave. No, just kidding. Okay, so we're going to talk about vector similarity searches. Sorry. So I think that, has anyone here heard about vector similarity stores? Cool. I know that if you sum like all the hands raised up, it doesn't really sum to one, right? So has anyone didn't hear about vector similarity searches? Cool. So we got like, I don't know, 10% participation. Okay, so first, this is our agenda for today. First, we're going to introduce myself and Argmax, the company that I founded that does recommendation systems. As Bracha mentioned, we are like 5 out of the 2,000 people in Israel doing that. So, and by the way, those are great meetups. So it's great to do a shout out. First, we'll introduce ourselves. Then we'll talk about why do we even care about recommendation systems and search? And why do I think those are the same thing these days? Then we'll talk about approximate nearest neighbors and why do we need to approximate in the first place? Then we'll talk about similarity search stores and some of the well-known vendors. Then we'll talk about how I see the new standard that's coming into existence regarding vector similarity stores. And then we'll finish with a short Q&A session. Cool. So this is me and my sons and my dog. My wife is kind of absent from the picture, but she's alive and all well. I'm leading Argmax ML, a consulting company that specializes in recommendation systems. And aside from that, I also host a podcast, Explainable with Mir Naveh, and that's try to cover all aspects of machine learning from a bird's eye view in Hebrew. I also co-organize the Pi Data, not to be confused with Y Data, meetup group. And essentially, this is like covers 120% of my time. A few words about my history. I started doing machine learning back at the time at Microsoft at the Kinect division. If you know that the Kinect was the 3D sensing device that didn't really work. And this was my segue into computer vision, but the classic computer vision, like before deep learning was a thing. I think that anyone who had anything to do with 3D sensing kind of decided not to do that anymore since deep learning really came up to our lives. After that, I spent a few years at AT&T working on customer support data. This was my segue into NLP, natural language processing. And I worked on Yahoo native ads. And I think that these days Yahoo and Taboola are almost the same thing, right? So I'm kind of local, never mind. Working at Yahoo was a huge experience because I got to do something that I will never get to do again. So I got to have like an SQL query interface to all of people's like personal emails, which I don't know if that's like legal anymore, without of privacy concerns. But yeah, that was lots of fun, like training models on huge data. And after I got the appetite to work on natural language processing, I co-founded Best Practice, which was a startup that tries to use NLP methods on legal documents. The end of the story is that we got acquired, and my co-founder is still like in the States. And actually, analyzing legal documents is easier than you think. There's a lot of structure, right? And also, it helps that lawyers are not that creative, to say the least. Okay. After the acquisition, I founded Argmax ML, a consulting firm, and this is what I do ever since. So as I said, in Argmax, we do search and recommendation, and these are like a subset of our customers. The way I see it, there are several clusters. Like we have the e-commerce guys, we have a lot of creator economy companies, and the majority of our clientele is essentially has something to do with advertising, publishers, advertisers, SSPs, DSPs. Now, if you see all of these companies, you don't see a lot in common, right? Those guys are selling items and those guys are selling ads, and this is great economy. But from our perspective, those are just the same thing from an architectural perspective. They all do search and recommendation, right? So a lot of cool things, a lot of cool domains to work on, but the underlying infrastructure is the same, and vector similarity search has a lot to do with that. Okay, so let's give a very short and inaccurate definition on what is a recommendation system. So this is like the simplest way you can define a recommendation system. You have a lot of users, and they have their own features, right? Age, gender, country. You have a lot of items, and they also have a lot of features. But you have limited space, and you need to make an informed decision which items do you display to which users such that something would be optimized. Clicks, installs, money spent. You have some KPI in mind, and you have limited space to optimize for that. Cool. So when we think about recommendation systems, the first use case that pops into mind is like shopping in a supermarket. So let's assume that we have this imaginary matrix. In real life, it's like huge and you can't really store it in memory. But let's play pretend that we can. And here we have like all of the users. And in the columns, we have all of the possible items. In theory, there's like a matching matrix, like whether this specific user would like that specific item. In practice, we usually try not to represent the data as users, but as user segments or as some kind of combination of features. Sometimes we do the same for the items, sometimes we don't. But we can think about as percentages. For example, what is the chance that John here would click or would buy the cookie jar? Now, representing this matrix as memory is not really feasible, and it's not something you can generally do. So the most common strategy is to represent items as vectors and users as vectors, such that their multiplication would be the conversion rate that we care about, right? So if we are able to do this kind of thing, this kind of magical manipulation, then we can use it actually twice. First of all, we can recommend users to items, right? But another cool side effect is that we can also recommend similar items. And almost every retailer website has either people like you bought, I don't know, cookies, popsicles, whatever, or people who bought an ice cream would also buy. So you have similar items and the for you recommendation. Those are two very common use cases that usually go hand in hand. So how do we learn these vectors? So this is a very good question. Thank you for asking. And we will not be answering this in this talk because you can teach a lot of courses and do your masters on how to do the best way to embed and to learn these vectors. So let's assume that we just got them from someone. But just to say a few words, still, you're all here and I want you to learn something from this talk. Then, grossly speaking, there are two strategies. On the one extreme, we have content filtering, which is trying to represent the item features. For example, if we're talking about a cookie jar, is it vegan? Is it keto? Is it a dairy? Right? And you can try and go feature by feature, either embed it or represent it with a one-hot encoding or any other kind of encoding, and then concatenate all of these features together or do some fancier embedding, but taking into account only the features. On the other extreme, we can think about the user behaviors, right? And this extreme is called the collaborative filtering, in which we don't really care about the user items. We don't really care about the items, we care about the user-item interaction. In real life, in most use cases, we do something in the middle. some sort of a collaborative element plus a content filtering element. But these are like the two extremes on how to represent items as vectors. So assuming that we have this magical encoder that takes into account a query or an item and encodes it into a vector, and you can see that it's a vector because it has this neat arrow, then search is essentially a pretty simple thing, right? We encode the query, we encode the item, we have a score. All we have left to do is to find the item that maximizes the score pretty fast, which is actually not that simple, and that's it, right? We have a search engine. And personalized search is essentially the same thing, but now we also encode the user features. Like where is the user from, what is his last previously purchased items or preferences or whatever. Right, so this is like a very general scheme for personalized search. Now, just to sum up, any way you try to look at it, we have a lot of vectors. We might sum them together, we might concatenate them, we might encode them, but this is a vector play, right? Now, let's talk a bit about what do we do with these vectors. So, essentially we have a vector and we need to find the k nearest neighbors. Anybody here not familiar with the k nearest neighbors algorithm? Cool. So scikit-learn has like k nearest neighbors built in, and that's it, right? Problem solved. We have like, I don't know, 4 lines of code here. We're using scikit-learn, and that is it, right? Wrong. Essentially, trying to do this at scale is not that trivial. Let's assume that I have m queries. I'm trying to serve like m users at the moment, and I have n items in my repository, and I'm trying to do k recommendations for each of them. So these are a lot of floating point operations, a lot of multiplications, a lot of ranking. Sorting is also not as cheap at scale. So working with the naive approach is not very practical when we're talking about large scale. So what do we actually do? So working with the naive approach has its advantages. First of all, it's the most accurate thing you can do. It doesn't scale. And if your data is small enough, then this is all you really need, right? So for some of you, this is like, you can live here. It might be good enough if you're talking about a few thousand samples. But if you're talking about advertising or very large retailers, then the query process might take a while. So we usually try to approximate the search and sacrifice accuracy for performance. There are 3 major strategies. There are more than 3 strategies, but we're going to cover like the most popular one. And the first one, sorry, is using hierarchy. The idea behind the HNSW, hierarchical, nearest navigational small world algorithm, is to try and build like zip codes, to build hierarchy of location. So let's try and pretend we have a made-up example. We're trying to find the k nearest neighbors of John, and John is from Seattle. Cool. So there's no need to compare John to the entire world, right? There even is no need to compare him to the entire United States. We can zoom in and use this hierarchy and first look at his, for example, neighborhood, and then zip code, and then state, until we find enough items to cover all of the k items that we want to recover. And only if we didn't find enough items, like in the entire state, we can zoom out and search the entire United States. Now, can anyone think of how this very cool hierarchical representation can go wrong? Can you do some errors?
You mean models?
Right. So if John happens to be living, for example, on the border of Seattle and Oregon, it may be the case that all of John's neighbors are not from the same state, but we would never find it out, right? So we are going to make that sacrifice, and the HNSW algorithm does sacrifice recall at some percentage, but it is, I think, de facto standard these days. Another approach is to use reversed indices. This is very common when dealing with sparse vectors. The motivation for this algorithm actually came from NLP, natural language processing. In NLP, at least in classical NLP, before LLMs and deep learning, we used to represent a word as a one-hot vector, as a vector the size of the vocabulary with only one non-zero entry at a certain index, and a document with several non-zero entries depending on how many words it had. So if I want to look up all of the documents that have the hello world phrase in them, I would first filter out all of the documents that have hello, and then filter out all of the words that have a word, and then I could do a very quick intersection using hashing and only compare a smaller set. Now, this technique works when the vectors are sparse, right? And we're going to compare every entry. It's not very efficient. But essentially, we can do the same for any vector, right? It doesn't have to be words. And it doesn't really have to be sparse. I can cluster the vectors and then represent the vectors as some kind of assignment to the vectors, to these clusters, sorry. So this is the motivation behind the IVF algorithm. And the third family of algorithm is based on hashing. Now, a special case of hashing is what we call a locality sensitive hashing, which are hash functions that preserve some of the spatial properties. So two items, if they're projected with an LSH, then if they are close with the LSH distance, it will also be close with the original distance, original domain. So I think it's best explained with a small and simple example. So let's assume that I have these vectors, and I hash them by only taking a look at this sign, right? So John here is mapped into the minus plus plus hashing. It's a very small number of potential values, right? I can store that in memory. And hopefully, this is the assumption that we make, is that John's neighbors would also be mapped to the same hashing, to the same cell in the hashing table. And even if they don't, I can try and look at similar cells, and I know that this cell, the minus minus plus, is probably more closely related to this one, right? Now, this is all very approximate, and the LSH algorithm is by far the least accurate, but the fastest. So it's also a very popular algorithm for trying to optimize for speed. So let's try and compare all of these four alternatives. On the right hand or your left hand side, we have like the flat or naive search, which is the most accurate thing you can do because you're actually calculating the distances, right? So there's nothing more accurate than that, but it's also the most expensive, both in memory and in speed, right? We need to store all of the vectors in memory, so it's pretty expensive. On the other extreme, we have the hashing methods, which are the least accurate, but the fastest. And they are ideal when accuracy is less important than speed, right? In some use cases, we need to respond in a certain amount of time. So we need to do all the sacrifices we can. And in the middle, we have the HNSW, the hierarchical one, and the IVF. And they are both pretty good depending on the use case, whether the vectors are sparse or not. And actually, in most cases, it is worth checking both of them. There's no clear winner. Cool. So now we covered all of the underlying algorithm powering the similarity searches. Now let's talk about similarity search databases. If we have a similarity search in place, then we can have the following workflow to implement a recommendation system. For example, this is John, this is John's vector. I'm firing the k nearest neighbors query, and these are the items that John would probably like. Right, so very, very simple. Now, in most use cases, we also want to filter out things that are not really applicable. For example, if John really likes bagels, he eats them every day, but John is currently traveling to Germany, and the German retailer doesn't really offer bagels. Then, even if bagels are a perfect match, there's no really a reason to even search for that, right? So these kind of filters are called pre-filters because I know them in advance. And the most common implementation is just to index another instance of the vector similarity search for each possible partition. Right? For each possible partition, for example, geographical region. You can think about other partitions, for example, age. I don't want to display videos to users that are underage. There's no really need to search for that if I know that in advance. And these are really depend on business logic. But not all filters are known in advance. For example, maybe that product ran out of stock, right? A few minutes ago it was available and now it is no longer available. So usually we have another layer of post-filtering, also known as re-ranking, right? It can take into account things that are more expensive to compute. So for example, if, let's see, the popsicles ran out of stock, then we need to filter them after the queries. Usually, we query more items than we need. If we need to display, for example, 12 items to the users, we would query 30, and then try to filter out according to business logic. This is one type of architecture. Now, there are plenty of vector similarity stores, really a lot. All of them are great. I'm not getting paid by anyone to say that they're great. But if you do, no, just kidding. So I got a chance to work with several of these for several clients. And I think that vector similarity searches are going to be a commodity. We see them implemented in Mongo, which I think is not listed here, and Postgres. And there isn't really a reason why any database won't implement his own vector similarity search. I can say that Vespa AI and Pinecone are both like in the near history, like a product of a lot of years of research at Yahoo and Amazon are pretty mature. There are a lot of newcomers, and they are all trying to figure out how to search things fast, on scale, and how to implement filters. Whether it's pre-filters, post-filters, there's a lot of logic that goes into retrieving those items fast. And there are benchmarks. For example, there's the annbenchmark.com, don't be confused. All of the vector similarity stores listed here are open source, so I don't think you'll find Pinecone here. But you can really compare, like, what is the precision, what is the recall according to the number of queries per second. You can choose the right one according to your use case. Cool. So there are a lot of considerations when choosing a vector similarity store. For example, are the items changing over time? Right. So if I recommend a live streamer that goes into broadcast like every day, it might be showing different content. Then I need to re-index pretty quickly, and I need to update the items as we go. Do I need to delete items, or are they like stored for good? Like in retail, usually items stay there. Are the vectors sparse or not? What is the memory consumption? As we've seen, like with the algorithm, there's a lot of trade-off. Do I do a lot of pre-filtering, post-filtering? All of this consideration need to be considered when choosing the vendor. And I think that the most important one is, am I going to do live inference online or on a batch, on batches? So these are like the main considerations. And now this is totally like my perspective on this whole world. I think that vector similarity is going to be a commodity. And like when we choose a database, we don't really care whether it's Postgres or MySQL or Oracle, because they all support pretty much the same SQL syntax. I think we're going to encounter the same world pretty soon. So the API is pretty clear. Here's a vector. Here's the metric that I care about. Please give me the k nearest neighbors. Thank you. Right? So this is the API. And if you're designing a system with that in mind, then you want your vector similarity store to not to be a Catholic marriage, something that you can replace, right? So you want to build your APIs in such a way that you can switch for another vector similarity store if the need comes, right? If you want a lower memory footprint or anything else. So there are a lot of libraries. This is, for example, Python models that we wrote that tries to have a unified API for several vector similarity stores that we work with. It supports Elasticsearch, Redis, FICE, and another one. But we're not the only one thinking in this direction. For example, LangChain also supports even more vector similarity stores. And again, it's the same API, right? That just choose your vector similarity store, and the rest is pretty much being done for you. Okay, so to summarize, we've talked a bit about the algorithm. We have a trade-off between recall and performance that you need to think from a business perspective which one is more important. Choosing the right vector store depends on the use case, right? There are a lot of them, and we talked about the considerations. And we are seeing a new standard for search coming into existence, and try to make your infrastructure kind of agnostic to the specific vector store. And that's it. Thank you. Any questions?
In which use case would you use FICE, or would you use it as FICE as not as server?
FICE and not what?
When you use the vector search inside the static file and not as a server like SQL server, a live server.
In which use case would I use a vector search in files or
static file? Yeah.
in static files? I would never use it in static files. I'd probably use a vector similarity store. I thought you were mentioning FICE, which is another vector store, but actually my favorite. But never mind. Yeah.
Is it possible to get the vectors of items and both users with some metric factorization method like ALS or something like that?
So the question was, can you encode the vectors of items and user with algorithms like ALS? The answer is definitely. Right? I didn't go into too many details about what algorithms you should use and when, because first of all, I think it would be a much longer talk, and it really depends on the use case. And also, Bracha is here. But yeah. Yeah.
It's just a continuation, but like in your experience, like how sensitive it is, like all this vector search, is it sensitive to the way how sensitive it is to the way you encode the vectors? Like how much does it influence the metric and
So the question was, how does the vector representation influence the metric? And the answer is a lot. For example, if you try to use an LSH algorithm, usually you'd get like the best performance, but results are, So it really depends. Now, if you're doing like a use case in which performance is more important than the accuracy, like you need to do like real-time bidding or something that you need to be responding really quickly. But it's okay to make mistakes, then you're probably able to make this sacrifice.
So thanks for the talk. But I'm not really convinced that we won't be interested in the under the hood in the future. So I mean, especially as you said about the filtering. So I need some database that is asset compliant. That when if someone is, deleting 100 items that you don't need to compare because you're in a certain country. I mean, I'm not a DB expert, but I know there is a difference between Postgres and MySQL. So even as a data scientist, I will still think about if I want to use Postgres or MySQL, or want to go with Hive or Spark. And so and I'm really curious, which is something that I'm really going to learn about how Lucene is indexing vectors. It should be a very different logic than the other ones. And I was surprised that I didn't see Spark here. So I mean, I'm just saying that under the hood there are many things that could support, prevent, or maybe prevent issues that may arise in the calculation.
So I try to unpack.
Sorry, I was throwing
I try to unpack and rephrase what you said, like in the way I would like to answer. So, first of all, Spark is not a database. Regarding Lucene, Elasticsearch, and Solar are originally sparse vector searches. In later years, everyone supports everything, so they also support the dense vector search. I could say that those seem to be an afterthought. Like from performance, if you're going to do dense vector search, you're probably better off with Face or Vespa or any other vector database that were designed with dense vectors in the first hand. But these days, they all support everything. And hybrid search is also a thing. Sometimes the vectors you could represent them as both sparse and both dense. There are a lot of, you can be very creative. Now, regarding the underlying algorithm, yeah, sure. I don't know. For example, when I choose a database, a classical database, I don't really care between Postgres and MySQL. I guess that maybe I should, maybe people do care, but those people who are really experts would also need to get into the internals and know like how does the filtering algorithms come into existence. But the same way that I don't really know whether Postgres use AVL trees or red black trees or hashing tricks. I don't really know and I don't really care, right? Just this is my SQL query.
But if 100 items are, I mean, you need the picture that you see on the database has to reflect the real picture. So, I mean, I'm not an expert in this as well, but I know that if you want a real picture of how many items are there per country, per particular stock, and someone deleted some items, you don't want to compare them. And it may be an issue in terms of
you cannot bypass public theorem by using vector databases. The thing that will happen is you have to choose the right trade-off for what you're doing. He's talking about search algorithm.
So we got to the PAC theorem, so I think it's a good time to stop. Any other last question? Yeah.
The embedding of the person depends on the items.
So the question was whether the embedding of the user depends on the items. The answer is yes. There are plenty of techniques how to do this. One very trivial one is to represent a user as an average of the item that she bought, right? So that's like one technique. There are plenty more. I think let's stop with that. Do we have time for more questions?
Part of the model, is there any method of dimension reduction? The vector more simple, less dimension?
The question was, is there a dimension reduction in the algorithms? Yes. And there's also all of the tricks that you can think about, like how to make vectors smaller, like quantization. Like maybe we don't need all of these floating points. Maybe you can use only 4 bits. All of these tricks are being incorporated in some of the vector stores. So all of the techniques you can think about how to make vectors smaller are implemented in some of these vector stores. Okay, thank you.